Hello, viewers. Have you ever watched a live broadcast of a rocket launch? When the rocket is about to lift off, suddenly there's a pause. Pause. Do you feel very nervous? In fact, the rocket launch is not only ignition liftoff so simple, it hides behind a set of very strict safety command system. Today, we will go deep into the Vandenberg Space Base on the west coast of the United States to unveil the unknown safety code behind the rocket launch, to see why each launch needs to be repeatedly confirmed safe and sound before proceeding. When it comes to the launch site, we may think that it is just an open space for rockets to take off. But in fact, the core of the launch site is not a physical site, but a safety command system operated by a professional team and a number of organizations. The primary goal of this system is to prioritize public safety over mission success. The major launch sites in the United States include Vandenberg Space Base in California, which is part of the Space Launch Triangle 30 SLT-30. The most important launch hub on the West Coast, and Cape Canaveral Space Base in Florida, which is part of the Space Launch Triangle 45 SLT-45. These two bases are responsible for nearly the majority of U.S. rocket launches. In addition, there is NASA's Wallops Base in Virginia, Spaceport Pacific in Alaska, and SpaceX's Starport launch site operating in Texas. Each of these launch sites has its own strengths and caters to different types of launches. To successfully complete a launch, regardless of the launch site, multiple organizations are essential. In the case of a commercial launch, the launch site must work closely with the Federal Aviation Administration FAA to plan and issue launch airspace and flight restrictions, and complete launch license applications and approvals. At the same time, it must also link up with the Coast Guard to designate no navigation zones in the launch area, monitor vessel movements, and assist with evacuations. The ground security team is responsible for controlling the perimeter of the launch site and keeping uninvolved personnel out of the danger zone. And the launch service provider itself has to interface with all of these agencies, submitting a variety of compliance documents and security programs. Nothing less will do. In the case of government-led launch missions, such as military satellite launches or NASA's deep space exploration, the approval process is even more stringent. Additionally, there are specific Department of Defense or NASA regulations that need to be followed to ensure the safety and confidentiality of the mission. What some may not realize is that there is a super amount of paperwork to prepare for a rocket launch. And as Firefly's Justine Flynn says, it's not just the hardware and people that make the launch work, but the document review is also key. For a launch at a TAF base, the launch service provider needs to submit a large amount of documentation, including system design specifications, operational protocols, safety risk assessment reports, and personnel credentials to prove that it is fully compliant with the launch site and adheres to all the rules. These rules cover a wide range of issues, including the safety of rocket flights, the safety of the airspace and space environment, and matters such as personnel avoidance, hazardous area delineation, and emergency response. Only after all the documents have been reviewed and all the complicated matters have been properly dealt with will the launch site authorize the rocket to lift off. These seemingly boring preparations are actually an important foundation for a smooth rocket launch. Next, let's talk about the risk assessment of a rocket launch. Risk assessment is a core part of ensuring safety. People may think that launching a rocket must be a pursuit of zero risk, but this is not the case. The core of risk assessment is the use of quantitative data and the pursuit of high reliability with multiple consecutive 9 south after the decimal point, rather than absolute zero risk. Mathematically speaking, it is impossible to achieve zero risk. What a team of engineers can do is to minimize the risk. There are many variables to consider in risk assessment. For example, there is a need to monitor and assess in real time the possible impact on surrounding aircraft, trains, cars, ships, and other transportation. In addition, the launch history of the rocket itself needs to be considered. The assessment criteria for a new rocket launched for the first time is quite different from a mature rocket that has been launched dozens or even hundreds of times. According to data from the Space Launch Reliability Study 2025, for rocket families with more than 10 launches, the late success rate can be stabilized at more than 90%. For newer rockets, due to the lack of sufficient flight data, the assessment will be more stringent, and even details such as bolts will need to be scrutinized to ensure the reliability of each component. SpaceX is a typical example of how to optimize risk assessment by continuously accumulating data. Their Falcon 9 rockets are launched so frequently that as of December 2025, a booster called B1071 has completed 30 flight recoveries, making it one of the most reused boosters in the world. This high flight density has allowed them to statistically validate the rocket's probability of failure and continually optimize their risk assessment models, resulting in more launch approvals. For example, the Florida Polar orbit launch option was permanently blocked because of a 1960 Thor rocket crash that killed a cow in Cuba. But SpaceX eventually reopened the option with massive amounts of data proving that the risk was low enough. And with internationally coordinated support from the Federal Aviation Administration and the State Department. This speaks volumes about the importance of risk assessment data. If the launch mission involves overflying the airspace of another country, the risk assessment also needs to take into account international political and diplomatic considerations. This requires the launch site to take the lead in coordinating the relevant agencies to consult with other countries to ensure the legitimacy and safety of the launch trajectory. In practice, whether it is a commercial or government launch, trying to obtain a launch license requires rigorous scrutiny at a number of stages. Factors such as technology, safety, and environmental impact all need to be assessed, and risk assessment is at the heart of all of these processes, directly determining whether or not a launch mission can be authorized. After talking about risk assessment, the next factor to talk about that also has a huge impact on the launch is the weather. Many people may not be aware of the fact that when a rocket is launched, the tail flame has the potential to induce lightning. When this happens, the consequences are unimaginable. There have been a few cases in history where a launch has failed due to weather issues, the most famous of which was the November 1969 Apollo 12 mission. At that time, the rocket was suddenly struck by lightning twice after liftoff, causing the command module to malfunction and a critical situation with numerous false alarms on the control panel. Fortunately, ground controller John Aaron reacted quickly to find the failure mode from the simulated data, and instructed the astronauts to switch the switch of the signal conditioning equipment from the regular gear to the auxiliary gear, and switch to the backup power supply, which solved the problem and ensured that the astronauts were able to continue the mission safely. The incident also served as a wake-up call for the space sector, prompting NASA to develop stricter weather launch guidelines. In 1987, the Atlas Centaur 67 rocket lifted off with a Navy communications satellite and was struck by lightning, just 49 seconds in, causing the guidance and navigation system to fail, the rocket to yaw violently, and the mission to ultimately fail. After these two accidents, weather launch standards became more stringent. Now, rocket launches are subject to a series of meteorological rules. 1. No thunderstorms within 16 kilometers of the launch pad. 2. The need to avoid charged clouds and use equipment to measure the electrical charge. Delay launches in the event of an approaching lightning strike. Launches cannot be made within 8 kilometers of precipitation, unusual atmospheric conditions, or 5 kilometers of a thunderstorm remnant cloud. Visibility has to be 64 kilometers, and radar tracking has to ensure a cloud-topping altitude of 18 kilometers. There are also specific minimum temperature requirements for different rockets. The wind speed on the launch pad ground cannot exceed 55 kilometers per hour, and the wind conditions at high altitude must also meet the requirements. None of these criteria can be compromised. In order to accurately grasp the weather conditions, launch sites are equipped with comprehensive monitoring equipment and specialized meteorological teams. Take the Vandenberg base for example. The base has an independent weather station that integrates real-time data from all surrounding ground stations. radars, and even satellites, and is able to comprehensively monitor the weather conditions in the region. The base also launches weather balloons twice a day, and more when rockets are launched, in order to obtain data on wind fields in the upper atmosphere. The weather balloons have built-in GPS and are able to transmit data such as humidity, upper air wind speed, temperature, and dew point back to the monitoring equipment. Crews can track the balloon trajectory throughout the trip. These balloons usually fly to an altitude of 100,000 feet before breaking up. In addition, there are about 800 weather stations around the world that launch weather balloons at the same time every day at 2 points in time, 0 o'clock and 12 o'clock UTC. This allows global weather maps to be drawn, providing macro data to support the meteorological assessment of rocket launches. Meteorological data is useful for more than just determining whether a launch is possible. If an accident occurs with a rocket equipped with a solid rocket booster, it could result in the release of toxic substances. In such a case, the security authorities can use the wind field data obtained from the meteorological balloon to determine the path of diffusion of toxic gases and help people prepare for emergency evacuation and protection. In addition, when the rocket rises to the point of maximum atmospheric pressure, if the wind direction and speed at that altitude change too rapidly, that is, if the wind shear is too large, or if the wind force is too strong, it may be beyond the tolerance range of the rocket. In such cases, meteorological data can help assess the risk. The Vandenberg base has a weather officer named Addison Nichols, originally an Air Force captain turned civilian, who specializes in monitoring the weather and submitting meteorological assessments to the launch director. Their work, while little known, is directly related to launch safety. In addition to weather and risk assessment, the exclusion zone control of the launch site is also very important, which is the key to guaranteeing safety from space. Exclusion zone control mainly includes 3 aspects: airspace, maritime, and ground, each of which has a specialized team responsible for it. Only by working together can we ensure that there are no unrelated people and objects in the danger zone during the launch. First, let's talk about airspace control. The airspace safety officer also is responsible for monitoring air traffic in the airspace associated with the launch to ensure that no aircraft flies into the temporarily designated no-fly zone. Prior to a launch, the launch site issues a temporary flight restriction area (TFR) or notice to Aerospace Mission (NTAM), which clearly indicates the location of the no-fly zone and when it will be in effect, so that pilots can check it when planning their routes to avoid violations. ASO's workstations contain sophisticated monitoring systems, and the screen displays the dynamics of all air traffic in the airspace in real time. This is a bit like the FlightAware or FlightRadar 24 that people usually use. But the system used at the launch site is more comprehensive, integrating military radar data to monitor air targets in all directions and ensure absolute safety in the airspace. There have been cases before where an aircraft broke into a no-fly zone, causing a launch to be suspended or cancelled. With the increasing frequency of commercial spaceflight, airspace control cannot be taken lightly, even though most pilots understand the importance of avoiding launch airspace. Next comes maritime control, which is handled by maritime safety officers, MSOs. Their job is similar to air traffic control in that they are primarily responsible for monitoring vessel traffic and working closely with the Coast Guard to make sure that no vessels are staying or sailing in the restricted area. The Coast Guard issues a notice to mariners (NTM) prior to the launch, which provides vessel owners with information about the area of the no-navigation zone and the time it will be in effect, directing them to avoid it in advance. If a cruise ship is found to be heading towards the NTM during the countdown phase and the Coast Guard fails to evacuate it in time, a suspension order will be issued, postponing the launch to the next day. However, with the continuous improvement of the control system, there have been fewer and fewer launch cancellations or delays due to ships or airplanes intruding into the no-navigation zone. Ground control is also critical, primarily to ensure that people around and inside the base do not enter areas that are off limits. Vandenberg itself is a military area and already has many defense and control systems in place, but just to be sure, a dedicated ground safety officer is assigned to confirm that everyone, including base personnel, is in a safe area before the rockets are loaded with propellant. The ground safety officer will also set up additional road closures and barricades to clearly demarcate hazardous and safe areas to prevent uninvolved personnel from entering. Here's another special circumstance. Vandenberg's train line predates the base itself, so trains have priority. When a train enters the train protection zone, the regional surveillance officer contacts the train crew, informs them of the launch, and advises them to stop or proceed. However, the final decision rests with the train. If the train decides to proceed, the launch site will adjust the launch process according to the actual situation. This demonstrates the strictness and flexibility of control in the restricted area. Each of these safety officers in charge of control will report to the launch site operations commander. The commander is stationed in the main control room, the launch site control center. This is the central hub of the West Coast launch site. The commander is required to consolidate all safety control information and report it to the launch decision-making body. Critical information such as meteorological data, airspace maritime dynamics, ground control conditions, and rocket technical status are received in real time by the launch site control center staff and submitted to the Launch Decision Authority (LDA), which makes the final launch authorization decision. Vandenberg's launch site operations commander, it Ballantyne and LT, Rocket, his real name is Rocket, said there are multiple tracking stations located around the base to monitor the rockets. If these malfunctioned, such as damage to the tracking stations or workstations linked to the flight abort system, it could lead to an unsafe situation, even if there was nothing wrong with the rocket itself. In such cases, the launch must be immediately suspended or put on emergency standby. There are many approval hurdles in the launch process. In the event of an unexpected situation like an equipment failure, the commander and safety officer need to work together to determine how to handle it. If the radar fails 3 hours before launch, the impact can still be assessed. But if the radar fails 2 seconds before launch, an immediate judgment must be made as to whether an emergency port is needed. This decision is directly related to safety. In order to ensure the smooth communication and execution of control instructions, the launch site has established a comprehensive set of specialized communication networks, the so-called nets. At a specific point in time before the launch, a release abort vote is conducted, the exact timing and format of which depends on the type of rocket. After the vote, if someone shouts pause, pause, pause over the communication network, it means that the day's launch is cancelled completely. If there is only a single pause, it means that the team pauses the countdown in order to solve specific problems. In the event of a serious situation, such as a mechanical failure of the rocket, a ground system problem, a launch zone violation, or a weather anomaly, the command pause, pause, pause will immediately terminate all launch-related processes for the day in order to avoid a dangerous situation. Next, I'd like to explain a common misconception about the flight termination system. You might think it's a self-destruct button that blows up the rocket when pressed right. In fact, the core objective of the flight termination system is to cut off thrust. When the rocket malfunctions, it allows the rocket to fly along a predetermined trajectory and eventually crash safely into a predetermined debris impact zone, avoiding injury to people and property on the ground. In addition, the operation of the flight termination system is carried out in the highly classified Mission Flight Control Center by a team of professionals, which is a double guarantee of the combination of manual decision-making and automatic control. The Mission Flight Control Center is so highly classified that even cameras are not allowed to be brought inside. Some of the rooms inside are top secret and electronic devices are completely prohibited. In the Mission Control Center, the team monitors the entire rocket launch process in real time. The core position is the Mission Flight Control Officer MFCO, who has the final say to terminate the launch if the rocket goes off track, and is the last line of defense to ensure safety. Although we can't take internal shots, We do know that the MIFCO's operations terminal has real-time video surveillance of the rocket, a timer, and a computerized display that is used to primarily monitor the rocket's trajectory and telemetry data. Among other key information, the flight termination system is able to function properly without a full range of monitoring tools. The control officer receives live video of the rocket launch through optical tracking equipment around the base. Some of the cameras use infrared technology to continuously track the rocket trajectory even in cloudy conditions, ensuring an accurate picture of the rocket's movements in complex meteorological conditions. In addition, the operator uses a foot switch rather than a button to turn on the communication system, which ensures uninterrupted radio calls and frees up his hands for other urgent tasks, making it a very user-friendly design. The operator's main concern is the trajectory line plotted in real time on the main screen. As the rocket accelerates, the trajectory line is constantly updated. At the same time, the computer calculates two critical boundary lines, the termination boundary line and the debris impact zone boundary line. The termination boundary line is a three-dimensional boundary that extends along a preset inverted cone trajectory. Once the rocket crosses this boundary line, the mission must be terminated immediately. The debris impact zone boundary line is used to define the fall range of the rocket debris to ensure that the debris does not extend beyond the safety zone. The calculation of these two boundary lines takes into account many variables, such as the rocket's speed, heading, material properties, and wind, and is much more complex than the trajectory simulations in the Kerbal Space program that you play, requiring large amounts of data to be received in real time and quickly calculated. Flight termination can be done in a variety of ways, not just by detonation. The simplest way is to just terminate thrust. For small rockets, the engine can be shut down manually, because its explosion power is relatively small, and after shutting down the engine can safely fall into a predetermined area. For rockets with solid rocket motors, thrust termination holes are designed. An explosive device is mounted on the engine case and detonated when it is necessary to terminate the flight, blowing out the hole to reduce the pressure in the combustion chamber and thus terminate the thrust. Another method is to use a linearly formed charge, which is a long strip of fuse that is mounted on the outside of the rocket. When detonated, it cuts through the fuel tank with such precision that it depressurizes the tank and cuts off the fuel supply to the engine, thus terminating the flight. For large rockets or rockets on special missions, high explosives such as C4 explosives are also placed at critical locations, usually at the bulkhead between the oxidizer and the fuel compartment. This ensures that the propellants are well mixed and burned before falling, avoiding secondary explosions from unburned propellants. There is also a special strategy called delayed termination. Not all failures require immediate termination. If the rocket has not yet crossed the termination boundary line, a delayed termination allows the rocket to transmit more data to the ground. Every millisecond of data flow is invaluable and may contain information from hundreds or even thousands of data channels, helping to analyze the cause of the failure and optimize the rocket design. In addition, delayed termination reduces the dispersion of debris. If termination occurs at an altitude of several kilometers, the area over which debris is dispersed will be much larger than in the case of a near-Earth explosion. Therefore, a properly delayed termination can reduce the impact on the ground environment while ensuring safety. Many launch sites now utilize an automatic flight termination system FTIS. This is a completely self-contained unit capable of automatically terminating the flight if the rocket goes off track, without human intervention. However, there are differences in AFTIS design for manned and unmanned missions. For unmanned missions, the FTIS design focuses on ensuring that no faulty rockets are missed. Whereas for manned missions, the FTIS design not only needs to be single-fault tolerant, but also needs to allow time for astronauts to escape in order to support human intervention. The AFTIS has multiple redundant systems to ensure the reliability of the termination process, combined with the sophisticated radar and artificial intelligence technology used at the launch site. This enables accurate tracking of rockets in real time. A significant advancement from the 1960s when only basic telemetry could be relied upon. Despite the automated systems, the MIFCO team continuously monitors the status of the rocket and intervenes when necessary to create a double guarantee. A real-life example illustrates the operation of the flight termination system well. On September 2, 2021, Firefly's Alpha rocket had its first launch. At that time, the rocket flew for about 15 seconds before the engine power connectors came loose, causing one of the engines to flame out. Nonetheless, the rocket continued to climb, albeit at a slower than expected rate, for 2 minutes and 30 seconds before losing control. Under maximum aerodynamic stress, the rocket tumbled like an acrobat, but amazingly, it remained largely intact until close to the termination boundary line, when the MIFCO system initiated the termination procedure. A replay from the mission's flight control center shows that the anomaly was broadcast in real time on the on-site communications channel, and crews closely monitored the status of the rocket in conjunction with telemetry data. Despite the pressure, the entire operation was so standardized that it can be considered textbook. Having said that, you should be able to understand that the core mission of the launch site is to balance public safety and mission success. It helps the rocket go smoothly from liftoff into its intended orbit by guaranteeing its tracking and communication. Throughout the entire process, the launch site is not only responsible for authorization and control, but also a key link connecting all aspects of the rocket launch, from pre-launch preparation to decision-making during the launch process. To post-launch tracking, the launch site is indispensable. The core hub of the launch site is the West Launch Site Operation and Control Center, also known as the Rocket Control Center. Key commands such as launch site cleared are issued from here. The staff integrates all kinds of data in real time to support launch decisions. Rocket tracking and communication are key to the success of the mission. For this reason, the launch site is equipped with a comprehensive ground station network and advanced communication equipment. The ground station actively tracks the rocket through a dual-axis targeting system, focuses the signal and locks onto the target to ensure smooth communication and, for the launch site to fulfill its mission, whether it's the PAF responsible engineer in charge of risk assessment, the launch meteorology officer in charge of monitoring meteorological data, the officials in charge of airspace and maritime safety control, or the MIFCO team in the Mission Control Center. Each of these positions carries a clear responsibility and strict standards. They all devote themselves to their respective jobs with a high sense of responsibility. Although their work is little known, it is directly related to the safety and success of the launch mission. For example, the launch site operations commander at Vandenberg, LT Rocket, whose real name is Rocket, with radar failure 2 seconds before launch. He was under tremendous psychological pressure to make quick judgments and decisive decisions with his safety officer. The ground station technicians, on the other hand, need to constantly monitor the status of the equipment to ensure stable operation of the tracking and communication systems. With the increase in launch frequency, the workload of the launch site is getting bigger and bigger. But its core mission and value have never changed. With the rapid development of commercial spaceflight, the launch site not only has to safeguard government-led space missions, but also provide efficient and professional services to commercial spaceflight enterprises, and promote the commercialization of space exploration. Launch sites have made space exploration safer and more organized, laying the foundation for mankind to explore farther into space. When the rocket successfully enters the predetermined orbit, the mission of the launch site is considered completed, and the follow-up is the responsibility of the launch service provider and the customer. But before that, the launch site has fulfilled its core responsibilities of keeping the public safe, supporting rocket liftoff, and ensuring mission success. Today, I have taken you on an in-depth look at the operational logic of the Vandenberg Space Base launch complex. I believe we all understand that space exploration requires not only cutting-edge technology, but also the quiet perseverance of countless behind-the-scenes personnel and the collaboration of various teams. The U.S. Space Forces and the Vandenberg staff used their rigor and pragmatism to guarantee launch mission. After launch mission, if you are interested in the aerospace field and would like to learn more about the ways to get into the field, you can check out the career page for the TAF. I hope today's content has given you a clearer picture of the safety and security behind rocket launches. If you enjoyed today's content, please like and subscribe. We'll bring you back next time to explore more space-related knowledge.